Okay, sorry. So I could not. So I disconnected because of some issues in the connectivity. So,
Hello, sir.
yes.
Sir, can you provide the notes that what you're teaching?
Notes are all from. So I am teaching from a book. This is Griffith. So I can write down the book. Uh,
We have IGNO books, but your handwritten notes is more perfect to learn for exam. That's why I'm asking. If you have any notes for
think if you look
MPH-3,
at my hand notes, they are not really good, right?
it's easy to
So,
understand because our exam is near, so that's why.
uh, but how can I give you the notes? To whom?
So we have group. I will add you in there. You can share it.
To the group. So if you give me the email ID, I can share the PDF.
Okay, sir. If I'm giving you a number, you can provide me in WhatsApp.
WhatsApp में अच्छा okay.
We have group. You can send either in group or to me. I will share it in my group.
Hmm, okay. Hmm. So I think better. I mean, I can give you these notes, but I don't think these notes I will be. Uh,
So
it
if
is
you could
better to
provide us
follow
some
because
important question also, if you will provide, that would be better.
that I can provide. The questions. I
Yes,
mean, look, questions will be from the book only. That is what I know. So if you go through the IGNO book,
because
then
we have that MPS-3 that will be 25 marks question will come.
Mhm. Yeah. So
So
one thing,
have
I
you seen
mean,
the previous year question of IGNO?
I haven't seen no, so I have no idea about the questions. So I can
Okay, sir.
only help you in the sense like if you want any particular topic to be covered
Mm.
in more detail, that I can do. Because right now I'm just giving you overview like in
Mm.
a space in a pace like we are still a slow pace, so time is limited.
Yes, sir.
A
That's why
lot
I'm
of
asking if
courses
you could
there.
provide some important question in perspective of our exam. That would be better, and if it would be easy for us to learn instead of
But I
notes.
have no idea about the question. So what kind of questions will be asked, and
Y- Yes, sir. I'm giving you my WhatsApp number. You just text me. I will provide you previous question. According to that, you can guess what question will come in our exam.
okay, yeah, you can do that. So I will just discuss few of the problems related to that
Okay, sir.
topic.
So just note down my number. Just text me. I will
Yeah.
provide you seven
Mhm.
double zero
700
899
899
0907.
0907. Okay, so
Yes,
seven
sir.
double zero 899 0907.
Yes, sir.
So
I
name
will provide you Hasibane.
Shibani. Okay.
I will provide you the assignment question. We have also a assignment question and
Mm-hmm.
previous year question, 2 year previous year question. I will provide you that. According to that, you can guess what question will come in our upcoming exam.
Mhm. Okay, okay, okay. Yeah. Keep- Okay, no problem. So then I can then mostly address those questions, like
Yes,
what are
sir.
the assignment problems and so on, so that you can
We
get
have only
ready for.
2 year question because that physics come into IGNO in 2023. So we have only 2 year question. So from that
Mhm.
you can know.
Yeah, yeah, that is fine. I think the question pattern
Only
will not
25
change.
marks will come. We have two paper at one day only. MPS-2 and MPS-3 in one day they are conducting this two paper exam. That is 25 marks
Mhm.
each.
Yeah, yeah, yeah. Yeah, I think if you prepare well, you can solve it. So
Yes,
then,
sir.
so let's at least right now. Today we will focus on what I have thought about, and then once you share those questions and things, so I can discuss those problems in the class. Okay.
Yes, sir.
Hmm. Okay. Or if you want any particular topic from electromagnetic theory or electrodynamics that you think we should spend a little bit more time? So
So
we
we
can
have
also do that.
exam where only few days left for exams. So if
Exam
important question
कब?
would be
When
better,
is the exam?
June 11, it will start from June 11.
June 11. Ah, okay.
Yes, sir.
June, no, still 1 month is there, no?
Yes, sir.
Right. Okay.
But we have
Okay, so
others
let's.
paper also, we prepare for that.
Mhm. Yeah, I understand. Okay, so the book that I am following, just give me a moment.
Sir, only teach us some important topics that are related will come in our exam. We don't need every topic to be discussed.
Hmm. Yeah, but I'm not aware of like what are the topics that you
Coming in exam,
so
yeah.
yeah, so you can give me the questions and then
So do you
once
have
I
IGNOU syllabus for MPS3 and MPS7?
have the syllabus, yes, yes.
Okay, okay.
But from that syllabus, like everything is there, right? It is not like
No syllabus. There are some limited question in syllabus. IGNOU has prepared something limited, not like regular course.
some limited questions.
Some
Question.
limited syllabus. It has been given in the
Yeah.
prospectus.
So
I
I will
was
also, I
checking.
mean, I will also stick to that syllabus only. But what
Yes,
I'm
sir.
introducing right now as will be used quite often. So that's why these things I'm discussing.
Yes, sir.
So these tools that we are going to discuss will be used like uh, in every like for the entire this electromagnetic theory as well as electrodynamics. So these divergence curl, then the divergence theorem, there is the Stokes theorem. So they will be used quite a lot. So that's why I'm just introducing it.
Okay, sir.
Okay.
Yes, sir.
Mhm. So, so the book I think IGNOU book is okay, but you can also follow this Griffith. This is Introduction to Electrodynamics. Okay, so this book also you can follow. Oh, sorry, so I'll keep it here so that if you want to take a note, you can take a note. So, similar to this vector differential. So these are all, this del operator is basically a differential operator. Okay, so this is a vector operator. So similarly, there are also integral that are involved, like you have line integral, you have surface integral, you have volume integral. So those things I think you are familiar with. So I'll go to the two important theorems that are used in electromagnetism related to this divergence and curl. So the first theorem is what we call as a Gauss's theorem. So it is also called as a divergence theorem or Green's theorem. So this is like the name, different names are given. And this is one of the fundamental theorem in electromagnetism. So this is also useful in other domains of physics, not only in electromagnetism. So if I take a vector and take a volume integral of the divergence, okay. So this is, I'm taking a divergence and taking the volume integral d tau. So this is a small volume element d tau. So d tau will be in your Cartesian coordinate will be dx, dy, dz, for example, will be equal to a surface integral, a closed surface integral, a capital A dot small t. So this is so the both the integrals are the same. So if I take the divergence of a vector over a small volume and integrate over a region, a volume V, so it will be same as the dot product of that vector to this unit vector or the area vector over the closed surface and the surface which closes that volume. Okay, so this is one of the fundamental theorem. So there are certain examples. So maybe we will do some examples tomorrow. Once I see these questions and like previous year questions or something, so we can solve some of those problems related to this. So the second theorem is also very important. So this is called as a Stokes theorem. So which is given by, if I take the curl of a vector over a surface S, it is the same thing if I take the line integral over line that encloses that surface. So this is the Stokes theorem. So these two theorems are fundamental theorems that are used quite often in electromagnetism. So they come from mathematics, of course, but they are extensively used in this electromagnetic theory. For example, the Stokes theorem. So if I take a surface, something like this, and I have a vector which has a curl like a rotation, something like this. Now I want to find out the integral over this surface. So it is the same thing if I find out what is the rotation over the line, this line that encloses this surface. This is a good enough. So they are the same thing. So I don't need to really calculate the curl of the vector within this surface for each at each area element dA. But if I just calculate what is the vector over this line that encloses that surface, that is good enough. So this symbol, it means a closed line integral. So similarly, in this case, this symbol means a closed surface. Okay, so this is what you have to be very careful about. Okay, so once I see these, as I said, the problems, I will solve some of those if it is required. If it is like in the question, you see those kind of things, then we'll solve that. Then another very interesting function that also we normally encounter, I think you might have already studied in mathematical physics, is the Dirac delta function. So if I have, let's say, a function, a vector function, so which is given by r cap by r square, and I take a divergence of this vector. So if you calculate the divergence, so you'll get it will be equal to 0. So you can use the Cartesian coordinate. Another thing which also I think I should not spend time on, but I should inform you. So these operators that we are writing, del. So I said it is x cap del by del x plus y cap del by del y plus z cap del by del z. So there are similar expressions also exist in spherical polar coordinates. So you must be familiar with this coordinate system, spherical polar and cylindrical. So if you are not familiar, tell me. So I'll just introduce it right now. Are you familiar with these coordinate systems?
Yes, sir.
Yes. Okay. So then what you need to do is you need to write this operator in this spherical polar coordinate. So for example, if a function is given in a spherical polar coordinate system. So you have to use the del operator, the appropriate form in that coordinate system, and then find out what will be the value. So here del dot v will be 0. So if you calculate that, and but if you calculate, if I take the same function and if I calculate this integral over a surface v dot, a closed surface v dot dA, this also you can do. So in that case, this area element, this dA, has to be written in spherical polar coordinate. So that also you can do. So dA in Cartesian will be dx dy, for example. But in spherical polar, it is given by r square sine theta d theta d phi r cap. So this is the area vector in spherical polar coordinates. So if you use that and with your function, so you will also find out this v dot dA will come out to be 4 pi. Okay, so which means if I enclose a surface around this v, so again, you go back to your divergence theorem. So the divergence theorem says if I take del dot v over dv, so or d tau over a volume should be equal to the enclosed. So v dot dA over the surface. This is what your divergence theorem tells you. But we see del dot v is 0. So this left hand side is 0, but right hand side is 4 pi. So this is a very contradictory thing. So now to address this issue, so that doesn't mean the divergence theorem is incorrect. So to address that issue, so what was done, like so a new function was needs to be here used, so which is called as a Dirac delta function, which you define as del x, which is equal to, let's say, in one dimension. So if it is 0 when x is not equal to 0 and infinity when x is equal to 0. So this is a kind of a distribution that was used, and this can be used to explain this behavior of a divergence that we have seen earlier. So in that case, so what you do is, I think I'll not spend too much time. So just to write down, so f of x. So for example, if I want to find out a function from minus infinity to infinity, so I will get, so it will just mirror its value at x equal to a, of a, something like that. So the divergence, like then what will be the divergence that we have seen? So how do you then write down the divergence? So del dot r cap by r square, so will be, can be written something like 4 pi del 3r. So this is your Dirac delta function in 3-dimensional. So this can be then address the issue that when r is equal to 0, so this will be equal to 4 pi, and when r is not equal to 0, it will be 0. So this Dirac delta function will be also quite useful in electrodynamics as well. Okay, so far we are still discussing about the tools that we are going to use. So let's now talk about the actual thing that we started with. That is how a charge distribution will affect the charge distribution, or how one particular charge or the charge distribution is going to affect the charges or other charges nearby. So in that case, what you call something as a source charge and another is a test charge. The source charge will be your charges which will produce the electric field or the forces, and the test charge will experience that field or the force. So again, so if I have a distribution of charges, so this is like I have several charges Q1, Q2, Q3, and so on, and I want to find out what is the force on this charge Q. So this is a test charge. So what is the force due to this charge distribution that we have seen here? So this is like what you can do is you can find out what is the force on capital Q due to Q1, what is the force on Q due to Q2. So you can just add up all those forces, so which we call as F equal to F1 plus F2 plus F3 and so on. If you just keep add all those, and what we call this is as a superposition principle. So this is a vector sum. So you add the forces vectorially, superposition principle, and then you'll get the net force due to all these charges on the test charge Q at which is at a certain distance R from the charge distribution. So this is what basically then led to our empirical formula that was given by Coulomb, which we call as the Coulomb's law. So Q, so for any charge Q and a test charge capital Q, so this force is given by, okay, so this is the Coulomb's law that you are aware of. Now, I said when we are talking about this interaction, so this interaction is not like a direct interaction or a physical interaction. So it is happening through some kind of another medium, let's say, not a medium, but another thread or something which is not seen. Okay. And what is that thread? So that we call as an electric field. So the electric field due to this charge will be given by, so which is F divided by Q. So which is given by 4 pi epsilon naught. So this will be capital Q, F divided by capital Q, which will be Q by R square R cap. So that means your force will be on any test charge is due to the Q multiplied by the electric field. So so that is how this charge, capital test charge, interacts with the charge Q through the electric field. Okay, so this is what the electric field is about. So now one can also define this electric field for different charge distribution, which will also follow the superposition principle. You can have it for a continuous charge distribution, volume charge distribution, line charge distribution, and so on. Now, one can also calculate for different charge distribution. So what is very useful in this while solving this kind of problems is use of something as called as a Gauss law. So this is a very useful tool to calculate the electric field due to a certain charge distribution. Also, it is not applicable for all cases, but it is a very useful tool. So, so what it tells us, this Gauss's law, that if I have a charge distribution, okay, and it produces an electric field, now the electric field that passes through a given area, okay, so dA, over a closed surface, over this closed surface S, will be equal to whatever this total charge enclosed within that surface divided by the epsilon. So this is what the Gauss's law tells you. So you can, so I'll give you an example so it will be clear how it will be useful in calculating the electric field. So if I take any closed surface, the flux through that surface, that flux means how much electric field is coming out from that region, will be given by this E dot dA. So that is a flux through the region coming out from the region S, which will be given by how many charges are enclosed within that surface divided by epsilon. So this is a very simple law which is very useful in calculating the electric charge due to a charge distribution. So, for example, so I'll take, so this will be quite clear if I give you this example, a problem. So we have, let's say, a uniformly charged sphere. So this is a uniformly charged sphere. Okay, so of radius, let's say r. So uniform charge means so the charges are distributed evenly or uniformly over the whole volume. So the total charge, let's say, is Q. Now, what is the electric field due to this solid charge sphere? So this is a uniformly charged sphere. This is a we will need to find out what is the electric field produced due to this uniformly charged sphere of radius r. This is a solid sphere has a radius r and charge total charge Q. So we have to divide. Now there will be two possibilities. So one is you can have an electric field outside the sphere and inside the sphere. Okay, so they can be same or different. So let's look at the situation when the electric field is outside the sphere. So in that case, we will say, let's say for we are looking at a situation. So this is the case one. So where we are looking at the electric field at any position r, which is in that case the r is greater than the radius of the sphere. Okay, so in that case, what we will do is how to use this Gauss's law. So what we will do, so we are interested in electric field at any position r due to the solid sphere. So we draw a surface, okay, so around this sphere. So this is what we call as a Gaussian surface. So if you draw that and then we apply the Gauss's law. So the law says E dot dA, so the flux of the electric field through this surface S, so we call this surface S, will be equal to 1 by epsilon Q enclosed. This is what we know. So this surface that we have drawn, it is an imaginary surface. It is not a real physical surface, but this is a imaginary surface that we have drawn around the sphere. So what will be the left-hand side? So the right-hand side is quite clear. Okay, so Q enclosed, how much charge is enclosed within the sphere? This is equal to the total charge, small q, divided by epsilon. That is quite clear. But we don't know what is the left-hand side will look like. Okay, so Okay, so to calculate this electric field, so the good thing is here, so we have a nice spherical distribution, charge distribution that helps us in using this formulation or using this Gauss law. So this is what we are going to use. So how do we calculate this E dot dA? So E dot dA, if you look at, we need to calculate the left hand side. So this is again, say, the magnitude and the angle, whatever the angle between the electric field and dA, what you are expecting. But we know the electric field. So the electric field due to this sphere, okay, so the electric field will be always going outward. Okay, so this is the direction of the electric field. And the surface that we have drawn, so the dA, the vector, so that is also always perpendicular to this surface. This is a dA vector, like wherever you go, so dA vector will be pointing outward as well. So this E vector and dA vector both point in the same direction. So that means this product, so theta will be 0, so it will be simply E, the magnitude of both this. Okay, so now if I look at this integral now, so E dot dA over the surface, this closed surface that we have drawn here, so will be E and dA, they are always perpendicular, and E is a constant, so I'll take it out from the integral and I will write this something like that. And what is the surface, total surface area of this Gaussian surface that we have drawn? So this dA would be simply equal to, it is a sphere, so the surface area will be equal to 4 pi r square. Okay, so this will be equal to 4 pi r square, and therefore the electric field, at least the magnitude of the electric field, will be given by divided by epsilon naught. That means electric field into this uniformly charged sphere will be simply Q by 4 pi epsilon naught. And the direction will be, so if I want to write down the direction, it will be always radially outward. So this is the good thing about a spherical distribution. So your electric field will be always in a radial direction. Okay, so you can just simply write, then the direction will be along r cap. So what it means now, this is exactly similar to, so let's say if I replace this solid sphere, so I said the solid sphere has a charge distribution and Q, and if I replace it, just a point charge Q here at the center of the sphere, so the expression for electric field will also exactly look like this. So that means when you go outside the sphere, okay, so it is as if the electric field is due to a charge which is sitting at the center. Okay, so there is no difference between whether the charge is uniformly distributed on a sphere or it is sitting at the center. So the electric field will be both the same. So the thing here is that using Gauss's law, if you did not use Gauss's law, instead of if you use only the Coulomb's law, it would be impossible to calculate, very difficult to calculate this electric field. But because of Gauss's law, so we could easily calculate it and quite fast. So the what are the situations when you should use the Gauss's law? So you will be using it only if the distribution has some symmetry. So if you have a line distribution or you have a cylindrical charge distribution or a spherical charge distribution. So in that case, you should be using these Gauss's law. So we'll use another example because this is also very interesting how this Gauss's law is useful. So I will take, so the problem is, okay, so we have an infinite plane, okay, which has a uniform surface charge sigma. So we have an infinite plane. So we are saying it is extending up to infinity. Now, what will be the electric field? Find its electric field. So what will be its electric field? So the situation is something like this. So we have an infinite. So this is extending to infinity on both sides. So this is a plane, XY plane, so to say. And we have to find out, so this has a surface charge sigma, and we want to find out what is the electric field due to this plane. So in this case, again, to use the Gauss's law here, so we need a Gaussian surface. Now we cannot draw a circle or because it is not a spherically symmetric structure, or not. You cannot also put a cylinder. So what you will create is a small rectangular region. So something like this we will create. Okay, so I'm drawing. So please bear with my drawing. So I'm drawing a box kind of thing as an area A. Okay, this area, this what we call as a Gaussian pillbox. Okay, so the name doesn't matter, but it is normally called as a Gaussian pillbox. So it is a small box kind of thing which we have created. Now you also create it. So you create this surface on both on the top and on the bottom. So if you look at this plane, so plane has two surfaces. Okay, one is the upper surface and one is the lower surface. So you will create this box so that it extends over. It has some extension over the top surface, and then similarly there will be also some extension on the bottom surface as well. Okay, so this is, so you will be creating a pillbox which is on the both sides of the surface. And then again, so on this surface we will be applying our Gauss's law. So here E dot, again the same thing, E dot dA over the closed pillbox surface will be equal to 1 by epsilon naught Q enclosed. So what will be the Q enclosed here? So it will be equal to, so the right hand side, what will be the right hand side? The right hand side is nothing but sigma into A. So we have a surface area of A, the surface charge density is sigma. So if I multiply, so that will be my Q enclosed. So this is not the right hand side, but Q enclosed. Q enclosed will be equal to sigma A. So the right hand side will be simply sigma A divided by epsilon. Okay, so this is what the right hand side. So now we need to calculate what is the left hand side. Okay, so now you look at this box and think about what will be the direction of electric field. Okay, so we need to calculate this E dot dA. If you look at it carefully, on the top surface, so what you have is, again, so the electric field will be coming out from the surface, okay, outward direction. And similarly, the dA vector on the surface A, so if I look at this face, Okay, so this has the area A. So the dA vector will be perpendicular here in this direction, and the electric field will be also in this direction. So if I have a sheet like this, so this is a uniform, everything is uniform. Therefore, the electric field will be also pointing in the upward direction. Okay, so in that case, again, they are parallel. Okay, so this left-hand side will be equal to E modulus of E, and then I'll take we have to take it over the closed surface area, which also extends on the top as well as on the bottom, so both sides, because this is what is very important. So you have a box, like you can think of, you have a sheet. Now on the sheet you have put a let's say a small matchbox kind of thing. Okay, so which is extending on both sides. So now matchbox, you have to look at the top surface and the bottom surface. And again, on the matchbox, you have also surfaces on the sides as well. So we haven't really think about what will be the contribution of these on this side. So if you look at now the area vector here, so this is perpendicular to the electric field. So this will all cancel out, all will be zero. So you'll have no contribution for the from the surfaces on the sides. Okay, so only the contribution will come from the top surface and the bottom surface. Now similarly on the bottom surface, so which is on the other side of the sheet, let's say, so their electric field is like this, and the dA is also in the same direction. So the dot product will be exactly the same as on the top surface. So E and dA, so dA is the magnitude will be here A. So the magnitude is A, the direction they are parallel. So this will be E into A from due to the top surface. So there will be also E into A from the bottom surface. So there will be two contributions. You will have two contributions. Okay. So now the left-hand side will be then equal. So you have one contribution from the top surface, one contribution from the bottom surface. Both have the same value. So it will be 2 magnitude of E into A. And this is the left-hand side, and the right-hand side is sigma A by epsilon naught. So your electric field, the magnitude, is simply equal to sigma by 2 epsilon. So the A and A will cancel out. So you have electric field is equal to sigma by 2 epsilon. And what will be the direction of the electric field? So the direction, we said it is outwards to the surface, so which is normally given by this n cap vector, which is a normal vector perpendicular to the surface. So this is the n cap in this direction. So similarly, in the bottom, you will also have an n cap as well. So this is the electric field due to this infinite plane has a charge density sigma, uniform surface charge. So what you notice here, that this does not depend at all on R. Okay, so this is a sigma which depends as a constant, that is for clear uniform surface density, and then epsilon naught, which is another constant. So it doesn't depend on R. Okay, so this is one observation I just want to point out. Okay, so this is how a Gauss's law can be used in different circumstances. Okay. So another extension of this idea is quite interesting. So if I put two planes, for example, so this is another example. So if I take two plates, I think these kind of questions might come up in the exam. So if I have two surfaces, one has a surface gas density plus sigma, another has minus sigma. And so these are again two infinite parallel planes. So these are infinite parallel planes. And we want to calculate what is the electric field. We want to find out the electric field in all these regions. So we have region 1, region 2, and region 3. So what will be the electric field here, here, and in this region? So this is what we need to calculate. So what we know, if I have the left, so this sheet or this parallel, this plane, so I have the electric field on all directions will be, the magnitude I know is given by, so what we call as E plus, let's say, this is given by sigma by 2 epsilon naught. And what will be the direction? So it will be the n cap, which is this direction. So this is E plus. So let me draw it here again. So I have these two planes. So due to this, I have E plus along this and E plus due to this. And also on this side, I have, so if I look at how the electric field in all three regions, so 1, 2, and 3. So this is E plus, this is E plus, this is E plus, but in this direction. So now, due to the other plane, so which has a charge density minus sigma. Okay. So what would be the, so due to the plane 2, so you have the magnitude minus, which will be given by minus sigma by 2 epsilon naught. Or in other words, so the direction of the electric field, so or let's just write down the electric field completely. So the it will be minus sigma by 2 epsilon naught n cap. So plane 2 for this one. So that means this electric field, the negative electric field, has the same magnitude, sigma by 2 epsilon naught, but opposite direction. So that means it will produce in this region a magnetic electric field in this direction and an electric field like this. In this case, also it will be an electric field in this direction. Okay, so the magnitude both have the same magnitude. So E plus the magnitude, E minus the magnitude is the same. So then what you can clearly see, so in region 3, they will cancel each other out. Region 1, they will cancel each other out. Only it will exist in region 2. Okay, so this total electric field, the total, here is 0, here it is also 0. So here E total will be equal to 2 E plus. Let's say you take the magnitude of E plus, so which will be given by sigma by epsilon naught. So this is sigma by 2 epsilon naught, so I'm multiplying 2. So this is the electric field within region 2. Okay. So that means if I take two such parallel plates having a uniform charge density sigma, so I will have only electric field within the two plates. So outside the place, electric field is 0. They will cancel each other out. This is also a very interesting problem which might be in your exam as well. Okay. One thing which, while using this Gauss's law, so we said we wrote it in a form which is something like an integral form. Okay, so if I go back, so this is what we call it in an integral form. Okay, so the Gauss's law in integral form. Okay, so one can write it in a differential form as well, which is also quite useful or very useful many times. So how do you write down the differential form? So I said E dot dA is equal to Q enclosed by epsilon naught. So you can do a little bit of 2-3 step mathematics, and then you will convert and use the divergence theorem. In fact, so use the divergence theorem that we discussed. So in that case, del dot E will be equal to rho by epsilon naught. So rho will be your, okay, again, sorry. So your rho, if I take a volume integral of rho, I will get Q enclosed. So the total charge enclosed within this volume V is given by rho deta. So if you use a bit of a 2-3 step, you will do use, and you can easily show this differential form of Gauss's law. So this is also Gauss's. And in fact, this is what is one of the first expression or equation of Maxwell's first equation. If you remember, I talked about 4 Maxwell's equations. This is the first equation. Del dot E is equal to rho by epsilon. So Maxwell, actually the first equation, most of the equations are not written by Maxwell, but he only compiled all together, and we'll see what is the reason a little bit later. But this is the first equation of Maxwell, which is also known as a Gauss's law. Okay, any questions so far? Okay, so another thing which also is quite useful, like when you are writing a electric field, we said a electric field due to a charge is given by 1 by 4 pi epsilon naught Q by R square R cap. This is a very general expression for the electric field. You can calculate the line integral of this electric field. Okay, so you define a line integral from one point to another point and find out what is the electric field due to this line integral. And what you will see is, if I take a closed line integral of this function, okay, so closed line integral, that is always will be equal to 0. This is also very important. So which again you can write also in a differential form. So this is the integral form. So the differential form will be curl of E will be equal to 0. Okay. So this is also important in electrostatic. Okay. So we are still talking about static charges, not a dynamic charge. So if the charges start moving, so this expression will change. So from here, from this particular expression, so a new something we can introduce a term which we call as a potential. So in mathematical physics, or even you can check here as well. So if I look at this expression curl of E equal to 0, and if I write, let's say E is equal to some gradient of a scalar. Okay. And if I now calculate the curl of E on both sides, so it will be equal to 0. So if a curl of a function is 0, so in that case, I can write that vector function as a gradient of a scalar. Okay, so this is again a well-known mathematical thing that the function that exists. So we can write electric field as a gradient of a scalar, and this scalar okay, yeah. So we can write this. So if you calculate curl of E on the left hand side is of course 0, and on the right hand side, so this also the curl of a gradient of a scalar is also 0. So that means so V is a scalar which we call as a potential. So this is not the potential energy. Okay, so it is a bit different from a potential energy. So how it is defined? So this potential is defined at a position R with respect to certain origin O. So this is similar to what you have defined potential energy for gravitation as well. Okay, so this potential V at any position R due to a charge distribution which has an electric field E is given by this integral. So where we have a minus sign, we start from a origin somewhere where we have defined a origin where we know what is the potential is. Then we take a line integral from that origin to this position R and calculate this integral E dot d. Okay, so this is what your potential V at a position R means. So this will be your reference point. So which normally you take it at infinity. Okay, so this is a very standard thing that is normally used in electrostatic. So you take the reference at infinity where you say that V will be 0, and then so your potential at any position R will be equal to the line integral E of dl from that point. So this will be used also quite a lot, these two relations. So E, E vector is equal to is a gradient of P, and similarly this one will be used quite a lot. Why we want to do that, this potential? So we will see, so the equations actually become much more simpler when you are dealing with V potential, which is a scalar. So earlier, if you write everything in a vector form, so you are a little bit, the life becomes difficult. But if you write things in scalar, so always very easy to solve it and use solve the differential equations and so on. So it is quite natural that in electrostatic, many of the problems are defined in terms of potential instead of in terms of electric field. So at least if we know what is the potential, so then we know if I take the gradient of that potential, so I can find out electric field. So if I have given a charge distribution, so ideally what my instinct should do is try to find out the potential due to that charge distribution. If I know what is the potential, so I can find out the electric field. If I know the electric field, I know what is the force, Coulomb force. Okay. If we have some example, okay, yeah. So we have a good example of here. So I take, so this will be the final thing, I think, before I wrap up. So if I have a spherical cell, so I have a spherical shell, okay? So it is not a uniform, a solid sphere, it is a spherical cell, has a charge density sigma, okay? And I want to find out, so it has a radius r. So a spherical cell means it is a cell, so inside is hollow. So only you have like a thin surface kind of thing exists and has a surface charge sigma. And we want to find the potential inside and outside. So what is the potential inside? So when R is less than R, and outside when R is greater than. If you use the Gauss's law for R greater than R, so you can find the electric field, so which will be given by 1 by 4 pi epsilon naught multiplied by whatever all the charges that are enclosed. So you can draw now a Gaussian surface, okay, so around this, and then the trick that we used, so you can use the same trick and you will get the electric field will be equal to Q by R square. So here Q, that is the total charge that is enclosed, will be sigma by 4 pi R square. Okay, so this is the surface charge density, and you multiply by the surface, so you get the total charge. So this is then to find out what is the V outside. So what we need to do, we need to now calculate this integral E dot dl from a reference point, and we can set this reference point at infinity, and we need to calculate this, okay? So you substitute this E, which is, so I'll take the 1 by 4 pi epsilon naught out. This is Q by R square. And dl vector is nothing but your dr vector, because we are talking about the radial direction here. So dl is, so electric field is also along the dr vector, so they will be parallel. So you have this expression. So you can now do the integration. So 1 over r square, the integration will be 1 over r, and you apply the appropriate limit, and what you will get is 1 by 4 pi epsilon naught Q by R. So this is the potential VR due to this charge distribution anywhere outside the cell. But inside the cell, this will be a bit tricky. So the inside, so when R is less than R, inside the cell, so VR will be equal to, so I will integrate now. So again, this one will common, I'll take it out. So ideally I have to, so let's say, what I will do is, so this is my here, so I need to calculate somewhere here what is inside the potential VR here. Okay, so this is what we are interested. So what we will do is, we will separate the limit. So it should be, I should take the limit from infinity to small r, but what we will do is, we'll take it up to the capital R, Q by R square dr, and then again, so 1 by 4 pi epsilon naught. So from R to small r, which is inside, and this is the electric field inside and dr. Now the electric field inside of the spherical cell, so E inside is 0. Okay, so due to this charge distribution, so this again you can calculate, so maybe I'll show it tomorrow how this electric field inside the cell is 0. And then, so this term will just cancel, will become 0. So your VR inside, so this is inside, let's say, will be equal to minus 1 by, sorry, so it will be plus again, so 1 by 4 pi epsilon naught Q by capital R. So it will be a constant. So outside, it varies as a function of R, but inside it is a constant. So it is a equipotential, so what we call it as an equipotential surface. So everywhere the potential is same. I'll discuss a bit more on this tomorrow because it's already time. So I will send a
So
message.
tomorrow at what time you will take the class?
4 o'clock. 4 o'clock. I'll
4
start
to
at
6.
Sorry?
4 to 6.
4 to 6. Yes. I'll try to be on time. So today there was because of this mock drill is going on, so I had to attend that. But tomorrow 4 o'clock. Okay.
Yes,
I'll
sir.
send a WhatsApp message to Sibani and.
Yes, sir. You just text me, I will send you.
Okay. Okay. Thank you then.
Thank you.
Thank you, sir.
Thank you, sir.
Stop sharing first.